Well, good afternoon. Did I get the microphone turned on all right? My name is Alan Ludwig. I'm a senior software development engineer here at Microsoft. I've been here, a little over 14 years. I will, just by way of excuse, say that my job every day is to come in and write code. And so I don't do a ton of speaking. And true to form, I procrastinated on a lot of my preparation. So we'll get to go through this talk together. I did get a chance to practice a couple of times, and my timing is just perfect. So I imagine now that I'm here in front of all you great people and I'm talking really fast, I may end up a little short. And so what I'm going to do is give you permission to stop me and ask questions, because I think I'll talk fast enough to allow for that. We're going to have 15 minutes for questions at the end, and then after the talk, what I'm going to do is if there's still folks who've got questions, we'll just sneak across the hall into the lounge over there at one of the ends, and we'll answer any questions that you might have. So with that, we'll go ahead and get started. Today I'm going to be talking about multi-language apps, and sort of I should start by saying what I mean by multi-language. It occurred to me that folks might actually be trying to do, sort of multiple natural languages, say, German, French, Dutch, and Mandarin. I'm actually talking about applications written in more than one programming language. My job here at Microsoft is to work on the Windows runtime, particularly that part of the system that helps you write your APIs once and consume them from C#, VB, C++, JavaScript. And in particular, the Windows runtime is what makes it possible for you to write your application and use more than one of these languages at the same time. So let me just take a second at the very beginning and talk about what I mean by the Windows runtime, because it's become one of those things that it takes its meaning from the context. And people talk about the Windows runtime from Microsoft, and they're talking about those thousands of operating system APIs that were brand new for Windows 8 that you can write to, and that's not what I'm talking about when I say the Windows runtime. And we've been calling our team the WinRT team for at least 3 years, and it turns out lately they've got this version of the operating system that they call WinRT that runs on the ARM slates, and that's not what I'm talking about. I'm really talking about this thing in the middle, this cross-language infrastructure that lets you write your APIs once and then consume them from any of those programming languages. So that's, when I say Windows runtime, that's the piece I'm talking about, and that's going to be the focus of our talk here today. So. And this, I think, is going to be the most controversial slide in my deck. So now that you can write your Windows applications in any language, the question comes up, well, what's the best language to write my Windows 8 application in? And just, for the sake of any sort of ethical dilemma, I'm a C++ programmer. I come in and write in C++ every day. But I'm not going to say that C++ is the best language to write your application in. In particular, the best language to write your application in is probably the language that you already know. For a lot of reasons, the best language to write in is the one that you're going to be the most productive in, and for me, that's the one I know. The language that your component's already written in. Most of us, I don't think, have very many opportunities in your career, at least I haven't in mine, to have a completely, green slate, completely clear slate. I just get to write every line of code, from scratch out of my head. That doesn't happen. Usually there's bits and pieces of components that you've already got, that you've already paid for, you've already invested in, you want to use them in your application. And for you, the language you've already got code written in is probably the best language. While it's true that you can consume Windows runtime APIs from JavaScript, you can't call Win32 APIs. There are some number of Win32 APIs which are marked modern and then you can call from your WinRT applications that are not WinRT APIs. And to do that, you're going to need to use you're going to have to go to C# or C# and use the interop facilities available to you, or go back into C++ and you can access them there. So sometimes the features you may need can limit your language choice some. Here it comes. the language that provides the right performance. And I'm not going to tell you that C++ is the language that you're going to have to write anything that you want to perform in. That's really not true. As we got to the end of Windows 8, I finished up my features early, and that gave me an opportunity to pitch in other places in the operating system. I had a chance to work with the IE10 team. I was working particularly on Canvas performance for Canvas-based games, and I got a chance to play around with code that was doing, all of its drawing in JavaScript, doing 2D and 3D games, and they got great frame rate. I mean, every time I've heard somebody say, well, you can't do that in Manage, or you can't do that in JavaScript, it's really only a matter of time before somebody does it, and it performs better than everybody thinks. That being said, sometimes you really are, splitting the atom or doing, one of these things that you absolutely have got to get, write the inline assembly for, and if you, need to go do that kind of thing, then maybe there's a language for that too, C++. So really, the right language for you to write your application in is the one that you choose, because there's a lot of cost benefit that goes into that. And it's not the language in the end, I think, that determines your choice. It's the business needs you've got. And some of that depends upon who's going to be working on it and what's their skills and, all the things that we've talked about. And I think for many, many applications, the right answer is going to be some combination of them. And that's really what I'm going to talk about, how to do that today. So, and that's it. How do I do that? And the answer is you write Windows runtime components. If you write a Windows runtime component in JavaScript, you can't write components in JavaScript. You can consume them in JavaScript. You write them in one of the .NET languages, C#, VB, or you write them in C++. You can consume them from any of them. So. And I'll let you know, I worked on the team that delivered this. The same cross-language infrastructure that we created in Windows to let all of the different feature teams within Windows write their APIs once and consume it in any of the languages, all of that facility is available to every one of you. You can go in and write your own components, write your own WinRT APIs, consume them from all of the different languages. That's part of the platform too. So. And why don't we take a look at what that looks like. So, ta-da. So what I've got here, most of what I've got 3 demos. There's 2 in the slides, and I'm going to see if I can slide in one more demo than I had originally in my slides. We'll see how well that works. But essentially, most of the demos I'm going to be showing you today are actual samples that you can get from the Developer Center up on the web. So this one happens to be the hybrid JavaScript and C++ sample. I think it was written by the Visual Studio team, and it was put up on the Developer Center after build last year, but it was up there for at least the release candidate of Windows 8 and whatnot. And it's kind of a nice example of a simple app that's got both a UI and a... See if I can make this a little bit bigger. Oh, nope, that pane doesn't do it. So what you're seeing in the right-hand pane here is there's 2 components. Up at the top, there's this JavaScript client, which has got the UI in it. And then down below here is a C++ component they've called imaging. And so let's take a look at what it does, and then maybe it'll make a little more sense what we're showing you. So here is the JavaScript UI, and we click Load Image, and there's the image from my speaker bio. And up it comes, and we hit Transform Image. And unfortunately, this is not the greatest image to show you this. The actual sample, what it is a cartoonifier, right? It has some edge detection in it, and it makes the edges really strong, and then it flattens out the color space. And apparently, I already have strong edges, and my color space is pretty flat already. So it doesn't do much. But when I was in the speaker room before, I just didn't have a lot of photos around that I could try it out. But it's kind of fun. It's kind of fun to play with. Make sure we're in the right spot here. So, but it's sort of a good example of how this is done. It's a very simple example too, so it's a kind of a good place to get your head around how to get started. So we'll start from the client side, and I just got to find it here. Well, I want the JavaScript. There it is, default.js. And we'll blow this up so you guys can see it back there. But essentially, there we'll look for the, not the load image, but the transform image. So in the transform image, maybe that's not too much of an eye exam. They've got this native object here. They new up this class one, and then they call transform image on it, and they pass a couple of file paths and a function for it to call back as it updates progress, and it just works. So they go, you write a component, and here's how you consume them. Your client goes in, news up the component, calls the interfaces, and off it goes. I'm focusing much more on the component side of the equation in this talk, so let's take a look a little bit about what they did inside the component itself. And this is really the interesting bit as far as this talk goes. This is the WinRT interface that they chose for this imaging component. And it's sort of cut off a bit there, but you can see they've just got this ref class. They carefully named class 1. And it's got a constructor and a single async operation which says transform image, and it takes the pair of files as its input and a callback function so that it can report progress. And so we can look a little bit about sort of how that was implemented, and they implemented it in a pretty simple way too. So here's the implementation of their async action, and they simply call this flat API. It's not even a class under the covers. They just call this flat API called transform image. Now under the covers, you guys can download this and take a look at it later, and I think it's kind of a fun little thing. My kids had a lot of fun with it. But underneath the covers, that one function that they call creates a class. It's got some helper objects. It pulls the thing in and decodes the image and plays with all the pixels and outputs it, but none of that complexity shows up in the interface. So they've really got this nice architectural laying going on where they've got the client on top. They've got a nice architectural separation at the component layer where they've got some simple interface they call in, and then once they get away from the WinRT interface underneath, it's just all C++. They don't bounce back and forth between them. And so that's kind of the frame I want to put you in for good component design. So let's talk about that a little bit. Oh, I forgot to set my clock. All right, so let's talk about that a little bit. How do you do good Windows runtime components? How do you make great ones? And I've got a couple of guidelines here, and we'll talk about each one of these in order. But really, you want to use the Windows runtime infrastructure only where you need it. You want to keep that set of interfaces nice and simple in order to make everything fast and fluid. So make sure you get that for your buzzword bingo. You're going to want to use the async pattern, and we're going to talk about issues that are going to come up as you start to do that. We're going to talk about for probably a third or half the talk about issues that will come up around threading when you start to do those things. So use the Windows runtime infrastructure only where you need it. There are costs to running across this infrastructure. Now, we've done a lot of work to make sure that those costs are minimized, right? And that generally speaking that you won't, you don't pay a huge penalty. But there are costs to going across this boundary, and I'm going to talk about those for a few minutes so that you have a sense of what they are and can accommodate that in your designs, right? And there's two primary ways where those costs come in. One is probably the less important of the two, is that Windows runtime interfaces are vtables, so they're indirect function calls. So in some theoretical sense, they are slower than a standard function call, because instead of just pushing the arguments on the stack and calling the function, you have to push the arguments on the stack, dereference through a vtable to find the address of the actual function you call. So if you're going to call this a million times, then you're going to have to pay the cost of the function dereference. This is exactly the same cost that you pay in C++ for having a virtual calling a virtual function. So it's no bigger or no less than that. It's exactly that cost. But it is a cost, so you should be aware of it. I don't think you'll necessarily see this so much in C# and JavaScript because they do this kind of dynamic redirection sort of for all of their objects. But in C++, you can certainly see and measure this. And it's exactly what you get for virtual base classes. The other one is type conversion. And this one can show up. We write our APIs once, and you guys get to write your APIs once, and you get to consume them in all these great languages. Well, all these great languages have very different type systems. They have a very different sense of what's a string. They have a very different sense of what's a number. They have a very different sense of what's a GUID, and on the list goes. And the goal of the Windows runtime, part of it at least, was to make the experience in your language choice natural and familiar. So there's another one for your buzzword bingo card. Natural and familiar. So in C++, you're going to use the types that are familiar to you. And in JavaScript, you're going to use the types that are familiar to you. What that means is at the WinRT boundary, you've got to convert those types. So we actually have a set of types that we use in the platform. And the language projections convert back to the platform types when calling a WinRT API. And coming out of the API, they're converted back into the type by the language projection, converts them back into the type that they're used for. So let's talk for a second about some of the interesting ones. And this isn't all of them, but I think this is most of them. I didn't go through and do an exhaustive search, but we can take a look. Strings, I think, is one of the really interesting ones because the WinRT type on the left, this is the type in the Windows runtime platform itself. And so at the boundaries, we'll convert to the WinRT type. In C++, it's platform string. And that's different than an H string. JavaScript has got vars, variant types. And it's a string inside there. And it's not the same as an H string, and it's not the same as a platform string. C# has their own representation for strings as well. And so you do convert to an H string on the way in and way out. I want to qualify this a little bit. We've got really efficient conversions to and from H string. None of those conversions actually require that you copy the string itself. So you never have to recopy the string itself. But H strings are these reference-counted immutable strings. And so there is this bit of control around that that's got sort of the length of the string and the reference count and a little bit of bookkeeping data. And then a pointer to the string. And that piece probably has to get created. Now you can do it on the stack or you can allocate it, but if you're going to push 10,000 strings across an API boundary, then you probably can measure the performance of that. GUID's another one that's interesting. I think C++ and C#, they keep GUIDs the same way everybody else does. JavaScript has no native type for GUID. So when we convert GUIDs in JavaScript, we convert them to a string representation. And when they come back, we convert them back to GUIDs. Integers, I've got one integer type in here. Generally speaking, C++, C#, their representation for integers and numbers is pretty much the same. The odd man out here is JavaScript, because JavaScript stores everything as doubles under the cover. I think they've got some facilities for 64-bit integers so that they don't lose things to rounding. But certainly JavaScript's got some work to do from its kinds of numbers. Datetime is another one that's interesting. It's very different in all three projections. I don't think there is a native type for C++. There certainly is one for the operating system. The operating system has this type it likes called file times, which are 64-bit integers. Date times are very, very similar to file times, but JavaScript and C# have a very different sense of what's a date. They use different epochs, they have different granularity, they've got different date ranges that they can express, and so they really are doing a conversion. Now these things aren't, no one of these things is going to cause your application not to perform. But it isn't sort of free to cross the boundary. There is type conversion going on. There are indirect function calls going on. So the cost is worth paying for the flexibility it gives you, but understand that there is a cost there, and so cross it when it gives you the value. Designing good Windows runtime interfaces is very similar to good object-oriented design. Windows runtime is not, WinRT interfaces are not really sort of the kinds of things that we would tell you, every object in your program should be a WinRT object. Don't do that. You won't be happy with the performance when you do that. WinRT is, you use it sort of on the component boundaries. I'm a C++ programmer, so I'm most familiar with that, and I would tell you, don't just go up to your C++ code and turn everything into an abstract base class and call everything through interfaces. You wouldn't do that. In the same way, WinRT is very much at that component boundary. Use it at the component boundaries, but once you're in C#, once you're in C++, use good design, good OO design, and keep WinRT at the interface. Yeah?
Does it mean that we should use C++ instead of C++ CX?
Really, that's entirely up to you. Both of them work very well. The operating system itself, all the code that I've written has been in sort of the low-level C++. There's a lot of heavy lifting that the language projection does for you. I've had a chance to play around a lot more recently with writing app code. I sort of like having exceptions. I sort of like having it automatically do a lot of the work for you. Performance-wise, I know exactly what the language projection is doing, and it's probably not doing anything more than you do manually in low level. So use the one you love.
By keeping it simple, you just mean that you should limit the number of interfaces.
It's the same thing we talk about in interface design, sort of in OO in general. He says, so by keep it simple, do you want to reduce the number of interfaces? And my answer is, good OO design is good OO design. So you want to make sure that your interfaces are abstract enough. They don't reveal everything about the implementation underneath. That lets you keep changing and improving and fixing bugs without breaking your clients. And none of this is specific to WinRT in general. What I'm trying to give you a sense of is how WinRT fits as fits into the design model generally. And so I can tell you absolutely, don't just run up to your C++ and make everything a ref class. Yeah, that won't make you happy. You'll end up paying for all of these, all these indirect method calls and all of these type conversions where there's no benefit to it. You're not actually intending that interface to be consumed outside. You're consuming it inside. So you want to keep it at the component boundaries. Does that make sense? Yeah.
Is there a reflection API to get into the WinRT components?
There is, because the metadata for WinRT is essentially the C# metadata. Yeah. I am reminded that there are good tools to read that from C#, and it's a little painful in C++. But it's exactly the same reflection APIs there have ever been.
Great.
So, yep. Async. Oh, I guess there's one more thing I should talk about. One of the reasons you might want to keep WinRT at the boundaries, and this turned out to be a big one in the sort of the prototyping that I did. Windows runtime interfaces only get to have Windows runtime types in them. And one of the things that means is that every pointer you've got in there has to be a pointer to a ref class. And so the WinRT, one of the things WinRT's got for it that makes it possible to be sort of cross-language is a very restricted type system. You may find if you just converted everything to a WinRT class, you'd suddenly be, not being able to go in C++, for example, and grab a pointer to a class. That then would have to be a ref class, and then suddenly everything's a ref class, and it gets to be a little viral, and so you want to keep that on the boundaries. You'll be happier if you do that. You can, but you'll be happier. Async. All right. So use the async pattern for long-running operations. The UI is single-threaded. UIs have always been thread-affine. You want to keep the application responsive, and really the way to do that is to use the async pattern. And here's a case where the language projections really sort of help you out. The async pattern in low-level C++ is fun. So the language projections actually make this quite easy. I'll mention, too, the other thing about the async pattern. The guidance we used when building the operating system itself was anything you thought that was going to take more than 50 milliseconds in any extreme case ever, you should go ahead and make async. And things that are async also tends to be a little bit viral. So you've got this method and it's synchronous and you're going to call it and it's going to return and you're going to call the next function and it calls the next function and it calls the next function. Down at the bottom there's an async operation. Yeah, async will then sort of have to bubble all the way back up to the top. So think about that as you're doing your interface design. If you think there's a reasonable chance that this non-asynchronous method could eventually call something that is asynchronous, you're going to want to go ahead and call it async from the start. So async operations, the language projections really do come out and make this easy. There's a whole bunch of ways to do async. What I'm going to show you here in the slides is sort of the simple one. You've got some lambda that you want, some little piece of code that you want to run in an asynchronous way. In C++, they've got the PPL library in there. You can wrap it up so that you can just throw your lambda on a task and it'll run on a worker thread for you. So, and there's equivalent, I'm not a huge C# expert, but there's an equivalent pattern in C#. They've got these tasks and essentially, again, you can just take your lambda and throw it on a task in C# and off you go. For more complicated things, there are other patterns that you can follow. But if you just got a bit of work that you need to throw on a thread, it really is just that easy. It's not just that easy in low-level C++, but it is here. So, and now we come to sort of the money bit of this talk, threading issues. So, writing UI, I think most people can, you call into a component, it's asynchronous, it doesn't block you, and so on and so forth. As you're actually writing components that get consumed by AI, there's sort of, this is the additional barrier, cost of entry, is you've got to be a little more mindful of these threading issues. And so writing really great WinRT components, you have to have some additional, some additional knowledge you've got to have, some extra things you've got to keep track of. So you want to mind your threads. And so here's sort of the talk of this. User interfaces in Windows have always been thread affine. They're always associated with a particular thread. And that's been true in Win32 forever. The old Win32 Windows in Win95 had associated with them a message pump that was associated with a thread. That's still, although we don't have thread message pumps anymore like that the same way. The user interface frameworks and the UI, whether we're talking about the DOM in JavaScript or we're talking about XAML, are still bound to a thread. And I just said you want to go use async everywhere, which means you're going to have the UI kick off some activity, which you're then going to take off the UI thread and throw it into some other process, which will fire an event or complete asynchronously, and somehow you've got to get back to the main thread to get the work done. And so I think I even got a picture of what that looks like. So to give you an idea, sort of more in pictures than in words, we've got a couple of swim lanes in here, and the swim lanes each represent a thread in the process. So you got the UI thread up on top in blue and the worker thread in orange. And so up top, you're going to call some asynchronous API. And it's going to, as it moves to the right, it's going to create a task, which is, some of that code on the last couple of slides ago. It'll go away and do work on the worker thread. Meanwhile, the UI thread is going to do something different. Later on, you complete this activity in the component, and it needs to update the UI. And then the question becomes, well, how do I get back to the UI thread to get work done? So how do we do that? And so we've got a couple of techniques that I'm going to talk about sort of for the rest of the talk today. We're going to talk about dispatching via the UI element. That's available to you for XAML. We're going to talk about dispatching via the core window. That's available in any case. But we've got an example of doing that for JavaScript, and we're going to talk about proxies and stubs. But this is the spot, I think, where I'm going to insert the extra demo. So we'll see how this goes. This wasn't in my slides. But here I've got a very simple component. It's a JavaScript. Again, JavaScript UI, C++ component in the back. The component is really, really simple. It's, let's see if we can. The component is really, really simple. Its interface looks like this. It's got a property called count. You can get it and set it. And there's an event that this interface exposes that says the count changed. Right? So you got a count, you can get it, you can set it. Every time you change it, it fires an event. Make sense? Right. And then for our JavaScript UI, we've got essentially, well, we'll just show it to you. For our JavaScript UI, we've got a little button that says "Click Me." I guess is that the new hello world for modern apps? It's "Click Me." You got "Click Me," and what's going on is in the UI there's a wow. That's an eye test. Okay, I should change my font in my demos. In the event handler for changed, we detect that it changed, and then we update the UI in the event handler. So it's sort of that easy, and we can take a look. So here is the code for. So here's the code for the set method. Is that you guys see that? Okay. So there's the code for the set method, and it checks, well, if your value comes in as value, and if it's different than the value I've got inside, update it, and fire the event. And this works out actually great. You just saw this code run. It runs just fine. When I said that UIs were thread-affine, probably what I should have also mentioned is that JavaScript itself is single-threaded and bound to its UI thread. So when you're dispatching back to JavaScript, it needs to be called on its same thread as well. And that is exactly what happens right here. JavaScript calls into the component on the UI thread. It comes into this. It fires the event. The event gets fired on that same UI, JavaScript's thread, and everything works. Of course, I did say that you want to use you want to fire this stuff asynchronously. So I apologize for cut and pasting code, but when I tried to type this in my practice sessions, we were going to be here till 4 o'clock. So what we said was you sort of want to write this code where you create a PPL task and you go do that, yeah, okay, changing the value of an integer is not a long-running task, but, give me some license. You want to do this. You want to say, all right, I'm going to throw this on a task thread and let it go. So let's see what happens when you try this. Wow, that's great. Now here's the beauty of this demo. There's a crash here, and it's supposed to be here. This is what happens. So we're going to talk about how to avoid this. If you're going to start writing components, at some point you're going to want to do a typed event handler, and somebody's going to call it from JavaScript, and it's going to crash. And you're going to get this really great exception, which says something like platform invalid cast exception. And honestly, nothing about that makes you think I should go write a proxy stub. But you've been here, and so by the time you get out of here today, you'll see this random crash, and you'll go, oh yeah, I should write a proxy stub for that. So, and that's going to be the punchline here. So we'll go ahead and go back to the slides. So the problem here is that JavaScript is thread-affine, and we just tried to call into a JavaScript delegate from something that wasn't the UI thread. And I'm going to give you 3 ways to go back and get to the thread. And at the end, I'll argue that probably the one that you want to use is proxies and stubs. But there are 2 ways to dispatch, and or you can write a proxy stub, and the system will then just do the work for you. It will just work. So for XAML in particular, so this is an example. Think about sort of the same. I pulled these off of sort of my own demo code, very much like this. And so output was the window where you'd update the count. And this is in the set method for the count. And you say, output here is actually a UI element, XAML UI element. And if you've got a UI element, one of the members of this element is this thing called the dispatcher. And it's got a couple of methods. The one here is has thread access. And what has thread access will tell you is, am I on the thread that can update this element? Because you're a component, you don't always know in what context you're going to get used, but in this case you can say, well, I was going to update the UI with this piece of code. Let me just check to make sure that I happen to be running on the right thread. And has thread access will tell you. It returns true when you're running on the thread that can update this particular UI. And so the code says, hey, I have thread access, I'm going to update the UI. If you don't happen to be on the right thread, then these same UI elements in that same dispatcher object has got to run async method. And so what we can do is down in the middle of this somewhere, you can see is just a lambda that updates the field, but it wraps it in this dispatch handler. So you create a dispatch handler and you call run async on the dispatch. By the way, I know we say that there's there's like an enum there that says Windows UI Core Dispatcher Priority Normal. Just pretend that's the only priority there is. Right? Don't use anything other than normal. But you can put the task back on the dispatcher for the UI element, and when the UI gets a second, it will go. There is a message loop for XAML pumping in the background, and it'll strip this message off, and then you will be on the right thread to update the UI. And so that's dispatching through the UI element. And that works. You can do that.
Quick question. Is there anything other than penalty if we directly run async would be called without checking if I am on the correct thread or not?
Is there any penalty? Yeah, you'll create this async object.
There could be performance penalty, but I mean, is there anything that would break if a piece of code would just call run async directly without checking?
No, you could just call run async directly. What you lose is some sense of when it happens. Of course, if you were counting on it happening right now and you weren't on the right thread, you'd have to run async anyway.
Well,
but you could do
like
that.
A post, right?
Yes. Yeah, very much like that. So the question, if I didn't mention enough, is, well, is there any penalty? Do we have to write this conditional code? Can we just always do the run async? You can realize you're creating an extra object and you're putting something on a queue to get executed later, but if that works, that's certainly simpler. So, all right, so that's one kind of dispatching you can do. The other kind of dispatching you can do doesn't require you to be holding on to a UI element at the time. And there is this core application inside of every what are we calling them? Windows 8 store apps. Inside of those things, there's a core application window. And you can just go call the thing. And again, I'm a C++ guy, so the code here is C++. There is equivalent C# code for this, and it looks almost like this, where you can just go grab Windows Application Model Core, Core Application, Main View, Core Window, and there's the dispatcher. And you can just call run async on that, and that will queue up to run that Lambda later on the main window. Now there's some things to be aware of with this. The core window that you get with this is the application's main window, which you'll notice is different than its sharing window or any sort of a picker window. So there are cases where you can't actually go do this. But if you're working in the main window, you can throw things back on the UI thread by dispatching through the core window, and it's available there as a set of statics. Fair enough. So those are great, and they're easy, and I can make them fit on one slide, and we'd be done. But in general, sort of the best way to do this is to get the platform to do this stuff sort of for you. And the reason why it doesn't is because it needs to have proxy stubs. So if proxy stubs are available, you don't have to do the dispatching, generally speaking. And I know a lot about the dark corners, and so there are always exceptions. But generally speaking, if you've got proxy stubs, the code that you wanted to write just works. So, and in particular, the case that you're most likely to run into that same crash that I showed you are typed event handlers versus event handlers. And so you might ask, well, why is that? Well, so event handler for uint32, I'll bet that one exists in the system someplace already. So there's probably already a proxy stub for it. But when you're throwing in your own custom interface in the typed event handler, like iDemoLib, whatever, your component was, and you're the sender for the event arg, you wrote that. There's not a proxy stub already produced by somebody else for you, so you'll have to write your own. But it's exactly this typed event handler that most people run into this very odd crash. So, of course, the other one I don't have a slide for is, well, if you can decide to use types that are common in the operating system, there may already be a proxy stub for those. At this point, I'm now warping your code in order to get it to work, so I'm not going to recommend that. But late at night, the day before the thing has to go live, and you're willing to live with turning it from a typed event handler to event handler rather than going through and putting in all the dispatchers, then that's between you and your code. So let's take a look at what it takes to create proxies and stubs for your Windows runtime components. And I would tell you this is really sort of, in a perfect world, what you'd like to do. I think at this point the best thing I can say is Visual Studio is not optimized for this particular sort of development. And I think you'll get a sense of what that's code for here in a minute. So we got about 5 minutes. So we'll see what we can do. So there already is, out there on the Developer Center, a pair of samples called Creating a Windows Runtime In-Process Component Sample. Isn't that a mouthful? Creating a Windows Runtime In-Process Component Sample. So you don't have to remember it. It's exactly the name I've given to the demo in the slide deck, and it's out there on the Dev Center now. And there's 2 of them. There's one for C++ CX, and there's one for C#. And what that really is a nice component sample, just like the one that Visual Studio did. The difference is this one actually has proxy stubs, builds the proxy stubs in it as part of the project. The reason why the one that Visual Studio did is they chose a type that already had proxy stubs in the operating system, so they lucked out. They picked their interface that they picked was something that was already in use someplace else, and so it worked. You may not be so lucky. So the more complicated sample that actually shows you how to do proxy stubs is exactly these. So it's a little more complicated. You'll see there's the WinRT component is this one, and I'm sorry for the eye test. I don't quite know how to make that particular pane bigger. But the bottom 2 one, there's actually the actual WinRT component. And then the 3 projects above that here are different clients. The one in bold is a JavaScript client. There's a C# client. There's a C++ client for this same server. And then down here in the bottom is the magic we're going to talk about, which is the proxy stub DLL. Now, if you've been a Windows developer for a while, proxy stubs really sounds like a COM thing, and it really is. WinRT is closely related to COM, and some of the it's COM plus a few more things. It's COM plus a restricted type system plus metadata, and that is what lets it be so wonderfully cross-language. But we still, under the covers, have some of those darker corners of COM, and proxy stubs are one of them. And so this is one of the places that it shows up. So, all right. So let's take a look at this. So, proxy stubs. The nice thing about them is you don't have to write the code for them yourself. There is a language for that. I'm going to find the file. There it is. The proxy stubs themselves are generated by the middle compiler, and the middle compiler takes idle as an input. And the nice thing to know about proxy stubs in WinRT is you don't even have to write the idle. The nice thing is you write your component. The metadata is generated automatically by the compiler. Underneath the covers, you can run a tool that reads the metadata and generates the IDL for you. And that tool ships as part of Visual Studio. In order to sort of wire the whole thing up, what you have to do is you add a post-build event. I know, I'm hearing the... You can run a post-build event which runs the tool, which is WinMD, WinMD IDLE. And I would make that a little bigger. It's a bit of an eye chart as well. So your normal component outputs metadata. So then the tip/trick that you're getting here is take your component, add a custom post-build step, and what you need, exactly the post-build step that you need to add is in this sample on the Dev Center. You know, go grab it, cut, paste, put it in your project. Runs this tool that turns the metadata into IDLE. You then come back, add a DLL to your component that consumes this IDLE as input and generates the proxy stubs. And I know that sounds simple. There's actually there are a few other steps in here. You'll need to add the right libraries because it pulls in some RPC libraries, and there is a define that you have to put in the preprocessor defines in order to get the right part of the RPC headers. And the best thing I can tell you to do, because I don't think I'll have a chance to go through sort of all of those steps, is you're going to want to get out WinDiff and sort of look at the MS build file for this sample and yours. And you'll get to see there's a few places to tweak. And the nice thing is you can do it all through the Visual Studio UI. But your template for doing that is really this project. But let me come back to the demo in the middle, where we talked about, you know, the code that you wanted to write. So here's my threading code, and I said, well, you can dispatch, and that works. So let me show you that dispatching works. So we don't have proxy stubs here, but we can dispatch. So here we'll dispatch through the core window, and that works. That's good. But the code you really wanted to write was this PPL task code. So let's put that back. This was the code you really wanted to write. You just wanted to throw the thing on a task and have it work. And you've seen that that crashes. So what we've done here is the same thing as you do in that other one. There is a custom build step, and we've added the threading lib.ps, and sort of the last place that you wouldn't know to look is that you have to register the proxy stubs, and that's done in the app manifest. So when you're, and this is sort of the last bit of magic which I think Visual Studio doesn't optimize for you, is once you've got your proxy stub library building, you need to come back and add the registration by hand. And so these particular GUIDs are available to you to find in the, in the generated code for the proxy stubs. They came from exactly our interfaces. They came from exactly our interfaces in here. So here are the three things that the IDLE generated proxy stubs for. And I registered the right ones in the app manifest. So here it's literally the typed event handler, ta-da, the typed event handler which we needed the proxy stub for to get things to work. So we added our proxy stub, we added the custom build step, we fixed up the libraries and imports, and we added the processor predefined, and then we added the registration in the app manifest for our proxy stubs. And now, that nice PPL code that you wanted to work in the first place without all the dispatching magic just works. So when you're writing your runtime components, there are some threading issues that you wouldn't necessarily run into as a UI developer, but now you've seen some of the magic that you can use to make that work well for you. So back to some of my early points, the same cross-legged infrastructure that we built for Windows to deliver its thousands of APIs and components in is fully available to you to write your own WinRT components. And to write great WinRT components, you sort of recognize that it's a technology that you want to put at the component boundary. You want to use it only where you need to. Keep your interfaces simple. Use that good object-oriented design. I don't think anything about all those things. Let that guide your thinking when you're designing your WinRT interfaces. As you're designing good WinRT interfaces, be a good citizen. Don't freeze the UI. Make your long-running tasks asynchronous. And I'd encourage you to go ahead and learn how to do that. Doing proxy stubs is painful the first time, but once you've gone through the sample and you've got it working for yourself, in general, you can write the code that you want to write, and it works right if you add your proxy stubs. So, other sessions, as I look through to take a look at other sessions I thought might have good information about writing Windows Runtime Component. The one from a couple of days ago, bring existing C++ code to Windows Store apps. I'm betting that was a really good component talk for C++. In preparing for this talk, I had a bit of a conversation with the folks who were doing the gaming case studies, where they actually, if I remember right, they were going to talk about a port of the Unity game engine over to WinRT. And a lot of that work was done in C#, so that would be the really good C# .NET based talk about how to write great components. That was going on this hour, so I'm afraid you missed that one, but go ahead and check that out online. And here at the back of my slide decks are links to the two samples up on the store, and I'll work with Build to get my other demo app. There's no magic in there, but I'll work with them to get my other demo app in so that it's available to download at some point in the future with the rest of the stuff from this talk. So, and then here's the standard slide for all of the other resources about sort of build and design and samples and videos and whatnot in general. So, questions?
Can you just put that last slide back up?
Sure. I think every talk, they gave this slide to me, so I think it may well be that every talk it's supposed to have this slide.
Yeah, I've seen before this.
So, sure.
Question. This proxy stub, can it be merged the same way as for COM it usually was possible to merge both proxy stub and same DLL?
Oh, can you merge the proxy stub DLL? Can you merge the proxy stub into your other DLL?
No, basically, in COM it was often.
Right.
Sometimes you need to do proxy stub, but you could just put some defines and tell, okay.
And it would automatically,
just do
yes.
Proxy stub, right?
I'm sure it's possible. The kind of Visual Studio jujitsu you'd need to pull in order to do that, I'm not terribly familiar with. So, in the OS, and there's probably no great secret, we use a command line system and we build up all of our build files by hand. And so we do merge our proxy stubs. So I know it's possible. We don't do anything in the operating system that you can't do with the other tools. But I'd be lying if I told you I knew how to do that in Visual Studio. But it is possible. There's nothing. It works. Proxy stubs are just COM objects. And so it's just a matter of getting them hooked up to the right entry points. To the right entry points in the DLL that hosts your WinRT component. So, exactly how you do that in Visual Studio, I don't know. So, back here.
Where do you look up if the proxies and stubs are already available?
That's tough. I don't know a good way to do it. In essence, the interfaces themselves, the ID for the interface is enough for the system to go look for the proxy stubs. So you could probably take the ID and go grunging through the registry to find if there is one. Identifying those is a little more difficult now that we've got these parameterized interfaces, you know, iProperties, iVector of int, and so there are a lot of interfaces, you know, there's a lot of interfaces in there that you can't necessarily identify just by looking at the GUID. So, but if you've got the ID for the interface you think you want there's a proxy stub for, you can, I'm sure you can go out on Bing and find out how to find where the proxy stub would be registered, and you can go look the same place. That didn't change. So, yeah.
Yeah, this may not be a question for you, but is it possible for a Windows Store app to create UI on more than one thread?
Is it possible for a Windows Store app to create UI on more than one thread? I know there are places where it's done. Like the picker is on a different window on a different thread. The share target is a different window on a different thread.
And all those charm things, I guess, are in the application, but on
The charms, I think, themselves are in the system.
oh, okay.
Right? So like Explorer pops out the charms, and then you click the button, and it does the work to activate the app, which is the target, and they talk to each other. Now, whether or not you can bring up another window, I don't know. I know, I write APIs. What do I know about? You don't want to see my UI. I mean, you've seen my UIs, and you don't want to see more of them. So, oh, back here.
So, could you just clarify, is the Visual Studio team committed to making it easier to generate the proxy stubs?
I honestly don't know. I work on the Windows side. I can tell you that they're aware of the issue. Yeah, I can tell you that they're aware of the issue. That much I do know. So.
We could just upgrade middle to be able to directly handle WinMP instead of just having to generate the IDL as an intermediate format in the first place.
That would be cool. All right. I won't hold the rest of you guys, but I'll tell you what I'm going to do. I'll go ahead and sneak across the hall and have a seat there if you've got questions. You know, come down up front, talk to me, or catch me afterwards. Thank you very much for coming by.